Yes, yes, sure. I will do that.
So, good evening, everyone. I am Sai, and I welcome you all to the fourth online free webinar on behalf of ARC Educators team. Now,
Okay,
ARC
Sai.
Educators is an initiative
You can start.
taken by amateur astronomers to promote astro. Okay, so ARC Educators is an initiative taken by amateur astronomers to promote and spread awareness about astronomy and astrophysics. We create curiosity in young minds by
Yes, yes.
organizing overnight stargazing programs, classroom workshops, and webinars. To know more about us, you can check
Yes.
our website by Googling our name, ARC Educators,
So, good evening,
and you
everyone.
can also connect
I'm
us
Sai,
on
and I
Facebook and
welcome you all
Instagram.
to the fourth online free webinar
So,
on
as you
behalf
all
of ARC
know,
Educators
today
team.
we have gathered here
Now,
to
ARC
celebrate the
Educators
Astronomy
is
Day.
an initiative taken
Astronomy
by
Day is
amateur
basically an event
astronomers
which is celebrated twice a year, once in a month of March and once in the month of September by astronomers throughout the globe. Uh, So, before we begin our webinar, I request all of you to follow some rules. So, rule number one is everyone is encouraged to note down their questions and doubts and drop them in the chat box. We will go through them, and after the webinar is over, we will start to answer as many as we can. And by
To know more
unmuting
about
the
us, you
individual
can check our
participants if
website by
required.
googling our name,
Now,
ARC
this also
Educators,
applies to all
and you can
those who
also
are
connect
catching
us
us
on
live
Facebook
from
and
YouTube and
Instagram.
Facebook. They may post their doubts
So,
in the
as you
comment
all
section. And rule number three is that follows rule one and two. So, without any further ado, I would like to introduce to all our very special guest speaker for today, Dr. Manojendu Choudhury. Dr. Manojendu has completed his master's in physics from IIT Delhi in 1997, followed by a PhD in astronomy from Tata Institute of Fundamental Research, Mumbai. Post that, he was a visiting fellow in National Center for. He has also worked as a research associate in Bhabha Atomic Research Center. He was a visiting fellow in Homi Bhabha Center for Science Education. He has also worked as a visiting faculty in Center for Excellence in Basic Sciences. He is also a resource person for International Olympiad in Astronomy and Astrophysics since past many years and was a team leader of Indian astronomy team in the year 2017. I'm sorry, he was the team leader of Indian astronomy team in the year 2019. Presently, he is the academic coordinator in Inter-University Center for Astronomy and Astrophysics, Pune. Now, this is such a wonderful experience to witness that all of us over here, we share common interest, right? We all love astronomy. So I'm sure everyone has looked up at the sky, at the night sky, and we may have observed many stars, planets, either through telescopes or through naked eyes. We may also have looked upon the internet for various pictures of stars and planets, galaxies, and supernovae. How fascinating are these? So, what do we see? With our naked eyes, we can only see seven colors. That is, the seven visible light, which forms a very narrow band of the entire electromagnetic spectrum. Apart from visible light, there is actually a whole lot of various bands of various wavelengths out there, which we cannot actually see. Our human eyes are practically blind to these wavelengths. Okay, so today we are going to look at our universe from all these different wavelengths and get to know about amazing stuff that's going out over there. So I'm sure everyone is as curious as I am to get to know about our multicolored universe. So without waiting any further, let's begin this journey. So Manesh sir, firstly, I am very glad to have you here with us today. I welcome you and hand over this talk to you. Sir, all yours.
Okay. I hope I am audible here. Fine. So, if you allow me to share the talk, okay, I'll just start sharing the slides.
So what do we see? With our naked eyes, we can only see seven colors. That is, the seven visible light, which forms a very narrow band of the entire electromagnetic spectrum.
So I'll just stop this video, my video screen, and I'll start sharing the slides with you. Okay? Yeah.
blind to these wavelengths. Okay. So today we are going to look at our universe from all these different wavelengths and get to know about amazing stuff that's going out
Okay.
over there.
So I hope
For
you can
everyone who has
see the
curiosity,
slides. Okay.
get to
The
know about.
title is Multicolor Universe.
So without wasting
Now,
time, let's
as
begin
it
this.
happens
So
that
Manojendu sir,
we perceive
firstly,
the universe around us with our senses. We have five senses, and perhaps the most dominant of those senses is the sense to see. We see around us, and we try to make sense of what is happening around us, what are the objects around us, how they are shaped, what their properties are, what they are up to. Okay, so and how they behave, and that is how we go around making sense of the world. Now, when we see things, there are many things we take for granted because we grew up with it. We have the senses, we grew up with those senses, and one of the fundamental sense is the sense of color. Now, what happens is when we talk about universe and we want to make sense of the universe around us, then we have to make sense of watercolors. And also, we give photographs, we see things, we share photographs, we share photographs of the scientific objects, scientific images and all. The first thing that we should understand and appreciate is that most of the images, the scientific images that we see, are actually false color images. This is something that I wanted to mention at the beginning. Please understand that what we see as our image may or may not be the actual color. Okay. Now, there are two pictures you see out here. Both are pictures of the same object. These are the Crab Nebula. This is a supernova remnant. The supernova happened about 1,000 years back, and this was one of the supernovae which was well documented in history, especially in Chinese history and other parts of the world. So we are aware of the history of this particular object. But whatever we see right here can be very confusing because the two images, they are actually not looking like each other. The structure is different, also the colors are different. So I will just mention at the outset that the images that we are seeing out here are false color images, and I have also added the word out here that it's a composite image. Both the images are composite images. What they are, we will understand at the fag end of this lecture. Okay, so please have patience. We will understand what do we mean by false color images and what we mean by composite images. Okay, now first thing first, just imagine that our eyes, or maybe more correctly our detector, our camera, they were sensitive to a more limited region of the spectrum than what we see. We can see from violet till red. But suppose our eyes were sensitive only in the green region, or our cameras, our detectors were able to see objects only in this green region. Okay. Now, somebody shot a photograph of this particular object, and then there were researchers trying to find out what this object looked like. I can assure you there will be different experts looking at the same object, with a lot of analysis, and there will be a lot of theories and hypotheses predicted about this particular object, and people will come to a certain conclusion. Okay, this object is something that we understand or don't understand, whatever. Now, suppose our ability to see other colors improved, okay, and we were able to see from the green to the red, and then we saw this same object in with a much wider perspective, with a much wider range of colors that we can see. And immediately we notice that when we increase our color range, we can see different structures. Different structures have different colors. And if we restrict our point of view to a narrow band, then we are actually seeing a very, very small aspect of it. As we broaden our point of view, I broaden our ability to see things, then we develop better understanding of what is the object, what is the nature of the object, what is happening around, okay, what is the structure. Basically, our knowledge is actually limited by how much we can observe. Okay, so that is why it is essential that we have a broader perspective, broader range when we look at any object, and that can apply to every situation in life. So we should try to understand the same object from different ranges of observability. Okay, now let's understand, what do we mean by colors? What is a color? If you see this picture actually contains 16 million pixels, and each pixel has a different color, slightly different color than its neighbor. All of these. Okay. Now what happens is that our eyes are able to resolve a few million colors, maybe at best around 10 million colors. That is a huge number. Okay. So if we expand these pixels and look at it, then we will be able to differentiate most of them from the not most of them, maybe half of them from their neighbors. Okay. Now, what we see as color is actually a manifestation of what happens in our eye. Light rays, which are also photons, they enter our eyes and interact with the nerves, and the nerves interpret these colors in a certain way, giving signal in our brain. And we understand these colors as something that we have seen before. If I'm if I am supposed to look at a color for the first time, it will be very difficult for me to appreciate it. But the fact is that we are conditioned to these nervous impulses since our childhood. And that is why we know that, okay, what is red and how it is different from orange and pink, and similarly how we move from one shade of color to another. But when we are trying to make sense of the world, that we are trying to understand the light that is being observed by us, by our eyes, or by our detectors like camera, let us understand something more fundamental first. Okay, now look at this picture, this image. This is one of those images which has a sun and the moon in the same frame. It's not, it doesn't always happen that you can get the sun and the moon in the same frame. And if we get them, normally one of them will be setting because they are separated. And I am sure that all of you know the main difference between the sun and the moon, even a child. who is not aware of energies, who is not aware of physics or anything. But even then, they can understand one thing, that the sun is actually a source of light. It is an emitter. Light or electromagnetic radiation, which is the more technical term for it, is being radiated by the sun. Whereas moon is visible to us because it is reflecting the light that is incident upon it from the sun. This is very simple, right? That one is an emitter and one is a reflector, or a more general term is scatterer. When you scatter light in one particular direction, it is reflection. When you scatter in all directions, it is, it is called diffuse scattering. So the similarity between the atmosphere around us, which gives us a blue sky, or at times it is, orange or red dominated sky at the horizon during the sunset, which this picture shows, the similarity, and the molecules on the surface of the solid moon, they are both receiving the light from the sun, scattering. Okay, so it is that when we make sense of the world around us, we should learn what is an emitter and what is a reflector or a scatterer, because our understanding of the nature of the object depends on that. For example, look at the temperature of the sun and the temperature of the moon. They both may appear whitish, yellowish, whitish under certain conditions. And you may assume that since moon is less bright, its temperature is less. But that is actually not the case. We will understand this in the subsequent slides in more detail. But the fact is that sun is emitting and the moon is reflecting. And that is why sun is at a higher temperature. Okay? Being an emitter, it has to have its own source of energy. A reflector or scatterer does not necessarily have its own source of energy as such. Okay? So now let's try to understand what is emission and how is light emitted. Now, light is emitted by charged particles. Okay, this you have to understand. What are charged particles? You know of electric charge. Okay, electric charge is a fundamental property of matter. A particle may be negatively charged or positively charged, and when a charged particle changes its energy, suppose it is at a higher energy, it has a lot of energy, electron has a high energy, and somehow it comes down to a level of lower energy, then the energy that it loses is actually emitted out as light, as photon. Now this picture image that you have in front of you is a very simplistic view of an atom, of few atoms actually. You can see the hydrogen, the helium and carbon. And the image that it gives here is that you have a positively charged nucleus, which is very dense, and you have negatively charged electrons moving around. Okay? Now, please understand that these electrons are actually not so simple. Although here we are showing them as small spherical particles, balls, which are moving around the nucleus, perhaps something similar to the planets moving around the sun, but the actual picture is much, much more complicated. Okay, this is the first picture that you get of the atom, but actually it is much, much more complicated, which I will not go into the details today. But what I have to emphasize today is that these electrons which are moving around the nucleus, they cannot exist at any particular energy. Okay, they have very discrete energy levels. You can see the steps out here, right? The ground state, then there are excited states. The ground state is the lowest level of energy for the electrons. Now, when the electron is at that level, it is the atom is in a kind of a steady state. If the electron goes to a higher level by some mechanism, then as it comes down, look at the picture here, from E2 to E1, if there's a transition shown by the arrow downward, then a photon comes out. The photon is shown by this wave-like arrow, wavy arrow, because photon is also a wave, and h nu is actually its energy. I mean, in this particular talk today, I will try not to involve any formula. I will just try to give pictures. But still there are moments that these some technical formula etc. will come. Okay, so just understand that h nu, h small h multiplied by this Greek letter nu, which is actually the frequency of the light, it gives me the energy of the light. Okay, now when the electron is falling from a higher level to a lower level, it is losing energy. Okay, just as a ball falling from a higher height to a lower altitude loses gravitational energy, here it is losing energy, and that energy is thrown out in the form of light. The other can also happen, the other direction of the flow of energy, that a photon or light can be incident on the electron, and this electron goes up to the higher energy level. Actually, that is how scattering happens, By some form of energy transfer, the electron at the lower level has to go to the higher level, and then it can come down. Okay, when this coming down is initiated by another photon, it is scattering. When this coming down is not initiated by another photon, it is emission. Okay, now we were talking about the discrete level. Now please understand this picture. This is nothing but a schematic of a discrete level. Look at these blue lines. Okay, these blue lines are, imagine they are like height. Okay, these blue lines are like heights, and these are at very discrete levels. When I say discrete levels, I mean that an object which is existing on a blue line can exist on the next blue line. It cannot exist in the in-between region. Okay, it is, for example, the steps when you climb a staircase. You can put your foot at one step, and you can put your foot at the next higher step, but you cannot put your foot in the middle. Your feet will be dangling in midair. Okay, so that is exactly how it is like. So this red object, when they're existing on a particular blue line, if it wants to move to the next blue line, it will have to climb that minimum distance that it is there. It cannot exist in the middle. But mind you, as long as it is in one of these blue lines, it can move left and right anywhere. Okay, so here, for the red squares, the red objects that you see, the vertical motion is discrete, but the horizontal motion is continuous. And we can say that the horizontal positions, the available positions for the red square, the red object, are in continuum, whereas the vertical positions are discrete. So now, any charged object like electron can exist in discrete levels, or it can exist in a continuum level. When it is existing in continuum level, then it can emit any amount of energy. But when it is making a transition from one discrete level to another discrete level, the amount of energy that is emitted is fixed. Okay. Now, in this figure, you look at the figure on the right, these are examples of energy levels available to electrons in molecules. Okay. These can be, the molecules have rotational levels. The molecules rotate. That means the charge on the molecules, they are rotating because of angular momentum. Then the molecules vibrate, like a pendulum or a spring. Because they have energy, they vibrate. And so those energy levels are also continuum when it comes to the vibration level of molecules. And then we have the electrostatic solution of the electrostatic potential, due to which we have the electron energy levels inside the bounds of the atom. Okay. So now there are many such discrete levels available for the charge distribution to exist and make a transition from one level to another level. And that is when light is emitted. Okay. So again, I am repeating this concept because this is very important for especially young students to understand that when and how light is emitted. Okay. So here you can see that we have at the bottom, look at the figure at the left, we have the zero level, then we have n equal to 1, then n equal to 2, and then higher levels, and the separation decreases, and then there's something called free carrier state. These free carrier states are actually continuum. There is nothing discrete about them. Okay. So when it comes to the continuum, then you see the electrons are free to go to any energy. One way to visualize the continuum state of electrons is electrons moving as a current in your conductor. When you switch on a light, you have a battery. You have the positive and the negative poles of a battery, and you light and connect some resistance to it, and the electric current flows through it. Now, those are the cases where the electron is not bound to any particular system, whether it's the electronic energy levels, bound electronic energy levels, or the vibration level, or the rotational level, or any bound state. Okay. So in that case, the electrons are free to move around, and the energy can be a continuum, not discrete. Okay. So now what happens is that, please understand one thing, that all the molecules that we see around us, every element, all the objects that we see around us are made up of these atoms and molecules. Okay. Even the gas is made up of that, and they are continuously emitting, okay, these lights. Now, every object behaves, the objects that we see around us normally, they behave something like a black body. You might have heard of the term. Senior students would have definitely heard of the term black body. Junior students may have heard the term, may not have heard the term, but let me give you a schematic or the concept of a black body. Okay. Now, please understand that the image that you see on the screen, it gives you the body, it is getting reflected on the surface, okay, and it cannot be seen. Now, this is a concept, please understand. A real situation will be like a solid or a very, imagine a very dense gas, something like that is inside the sun, where the gas is extremely dense. Then, how does this photon enter this black body? This photon doesn't enter, it is always created by the atoms, okay, or rather the charged particles in that dense gas, okay. And the photon that is created, the gas is so dense that light is not able to escape. Before it can escape out of the object like the sun, it is continuously getting scattered by another atom or molecule or a nucleus. Okay. So this continuous, the dense medium is not allowing light to escape. And this black body image is a concept of that. Okay. Photons are getting emitted and yet they are unable to escape and they keep on getting scattered. But then, because it is not infinitely dense, there are some cross section of escape, some photons escape, some light escape. Okay. And when we get some light out of this kind of an object, we say we are getting radiation from the black body. And that is known as the black body radiation. Now, understand one thing, that every object is has some energy, is at a particular temperature. You see, temperature is a condition that determines from where to where energy is flowing. Because energy will always flow from a high temperature region to a low temperature region. Okay. Now, any object which is at a non-zero temperature, like all the objects around us, okay, they actually have some inherent radiation happening inside, which is not escaping, and very little amount is escaping, and that radiation is black body radiation. Now, depending on the temperature, the nature of the radiation changes. Okay. Now look at this picture that we have around here. Okay. Please understand. Let's move from the left column figure that we have electrons and other charge distributions at different energy levels. They make a transition and they emit photon. This photon that is emitted behaves like the picture in the top, in the bottom right, because it keeps on getting scattered by different atoms. It behaves as if it is enclosed by a black body. Okay, that is black because it is not allowing any light to escape. Okay, and because it is not infinitely dense, just as some photon entered, some photon will exit also. Depending on the temperature, I will get a certain color of the emission that I'm getting. Okay, so this particular picture We will understand little bit more detail in subsequent slides also. But look at this. This particular figure is actually giving you the spectrum of a very famous law in physics, which is known as the Planck's law. Okay. As I said that I will not deal with formulae. So, you know, I will not give the mathematical formula, but please understand one thing, that as my temperature is increasing, look at this black curve. This black curve corresponds to the light that is emitted out of this black body. Okay. And depending on the temperature of the black body, you can see that the amount of light that I'm getting is increasing, because the curve is moving towards the top. Also, the curve is moving towards the left. Okay. Now, please understand the x-axis, the horizontal axis, which is giving me the wavelength of the light. And in this wavelength, we are looking at a very small region that is our eyes are sensitive to. Okay. And you can see that the emission that we are getting is peaking at a particular wavelength, 5500 Kelvin, which is nearly the temperature of the sun, is peaking in the green yellow region, whereas 3500 Kelvin is peaking in the red region. So if I look at an object which is an emitter and it is red in color, then it is at 3500 degrees Celsius. Okay. If it is at yellow green region, then it is something around 5000 degrees Celsius. So immediately you'll understand that there is a direct relation between the color of the light that I'm getting and the temperature of the body that I'm looking at. Okay. Now, Newton was able to break up the light using a prism into different colors, and he called them 7 colors. Now, honestly, I personally can never differentiate 7 colors. If I look at the spectrum at the top here, then I can distinguish 3 colors, the red region, the green region, and the blue region, and maybe 2 more boundary regions. Okay. But I personally find it very difficult to claim that there are 7 colors. And if you look at it, then there are actually infinite colors. So the 7 color is a very, very arbitrary number. Okay. You can talk in terms of regime, that this is what is happening. This is a range from here to here, from red to violet. I can see this range of colors. Okay. Also, you need to understand that light is something called electromagnetic wave. So basically, light is nothing but electric wave and magnetic wave vibrating. Okay, I will not spend too much of time on this because we have to understand the astronomy of it. Okay. Now, as it happens that the visible range that we see, from the red to the violet, which corresponds to 3500 degrees Celsius approximately, to around few tens of thousands of degrees Celsius. Okay. Here, this range is not the only range in which light is emitted by the object. Okay. At the lower energy, beyond red, we have something called the infrared. Then we have the microwave region, and then we have the radio waves. Mind you, these are all like light waves. It's just that our eyes are not sensitive to it. And on the higher energy end, from visible, we have the ultraviolet range, the X-rays, the gamma rays, and of course, gamma rays also we can have very high energy gamma rays and all. Okay, now these actually span a huge amount of energy scale. So first and foremost thing that you need to appreciate is that when we are looking at colors of an emitter, we are actually looking at the energy of the emitter, the temperature of the emitter. This is extremely crucial to understand. And again, I'll go back to the images that so the one image that we saw before, that of the sun and the moon. Okay, I am saying that sun is at yellow color, yellow green color, and it is at a temperature of 5,800 degrees Celsius. The surface of it. Inside the sun, it is much hotter, billion degrees, but that's a different story altogether. But the sun's surface is at nearly 6,000 degree Kelvin, and the moon is very cold. So example, when you look at a yellow flame of a candle, you cannot put your hand into it. But you look at any yellow color, you can dip your hand into it and touch the wall with yellow color. Because the paint, the wall, they are actually scattering the light. Okay, the light can be sun. I mean, the origin of the light can be sun, or the some electric bulb that we have, the fluorescent bulbs that we have, the torch light that we have. So here we have some other source of light which is getting scattered. So when it comes to scattering, then the property of scattering is very different from the property of emission. And this is very, very important to appreciate in order to understand the properties of the objects that we see. Okay. Now, let's look at just a glance at a galactic image at different wavelengths. Radio is at the lowest energy level. Then we have showing here the infrared sky, which is near the optical level. Okay. Then this is the optical image of the galaxy. Then you have the X-ray sky, and then we have the gamma ray sky. Okay. Now the first thing that you should notice out here is that the optical sky is actually more discrete in nature. Okay. Now this is due to one very big reason, that is the diffuse emission is very less in the optical regime. The source of the optical light that we see around us are the point objects called stars. Okay, they are the most dominant source. And that is why when you look at the radio sky and the infrared sky, okay, then they are appearing quite different because of the nature of the emission that we are seeing. Okay. Now, let's cover the electromagnetic regime one by one slowly. So let's look at the object that is nearest to us, which is our good old sun. Okay. And when we look at the sun, it appears like white light to us, very bright source of white light. The reason why it is white is that sun is kind of at the middle of the optical regime to which our eyes are sensitive to. So maybe man has been able to evolve the way we have because by chance our eyes evolved to make the best use of the sunlight. And so perhaps we were able to adapt to our environment better than other creatures. Because our eyes are sensitive to the middle of the range, the green range, we actually see same amount of blue light and the red light, kind of nearly same. And when you combine all of them together, we get the white light, which is a combination of all the lights that we have. Okay. Now on the right, what we have is the spectrum, that is as a function of wavelength, what is the intensity that I'm getting of the light. Okay. So spectrum, please understand, is that for a particular wavelength, how much of light am I getting? So when it comes to 500 nanometers, it is in the green region. Okay. Very high amount of light. But less than that, when I go to 600, 700 nanometers, which is I'm going to the red regime, okay, 1000 nanometers and all. Okay, 600, 700 nanometers is our 700 nanometers is kind of the limit to which we can see. We are going down in energy, and when we are moving towards left, towards 400 nanometers, 300 nanometers, then we are going to the violet region. Okay, so now from this picture, you can see that around 500 nanometers, the amount of light that I get is highest. Okay, this is a spectrum from the sun. Okay, so now you can see kind of at 700 the amount of light, 700 nanometers the amount of light that I get, and at 400 nanometers the amount of light that I get. They are the blue and the red extreme of our sensitivity. The amount of light is more or less the same. So they kind of combine equally together and we see a white light. Okay. Now at the same time, when we see an eclipse, okay, then what do you see? Eclipse happens when the moon covers the sun, the photosphere, and they see kind of a halo on the sun, which is weak in the optical light actually. Okay, and that is known as a corona. So the extent of the sun is actually not ending with the photosphere here, but it extends with at outside the photosphere also, which we can't see all the time because the amount of light that is coming from here is less. Okay, so this is another example of how we should broaden our horizon, broaden our perspective, and once we do that, we see different structures in the same object. In fact, I'll not go into much detail today, but this corona is actually emitting at maximum in the X-rays. So if we look at the corona here, then through in the X-rays we will get the maximum sensitivity. Let's learn again this concept of color and temperature. Okay, so as I am moving from a lower temperature body to a higher temperature body, you can see how my sensitivity to the color changes. Okay, now at the bottom, look at the spectrum, which is at 3000 degrees Celsius. Okay, the bottom left spectrum. Okay, now this bottom left spectrum, which is at 3000 degrees Celsius, it is actually peaking at 1000 nanometers. Okay, and that is in the infrared. Our eyes can't see it, right? And on the top, you can see at approximately 3500 what the spectrum looks like. Okay, and then at the top, look at the spectrum at the top. The different spectra correspond to different temperature, and you can see the peak of the spectrum is shifting in wavelength. What it means is that the light that I'm seeing predominantly is changing its color with temperature. Same thing is there at the bottom. As my temperature increases from 3000 degrees Celsius to 6000 to 10,000 Kelvin, you can see the peak of the light is changing from the infrared regime to the optical regime to the ultraviolet regime. At 12,000 Kelvin, the peak is at the ultraviolet regime. But still, from the curve, the black curve, you can see that there is enough light in the optical regime also. Okay. So now you see, by looking at the different composition of light, how much light I'm getting at different color. I'm sorry, the composition of light at different color, I can get a measure of the temperature. This is extremely crucial in astronomy. Okay. Now the same figure is now at the top. Okay. Different temperatures correspond to different type of colored light that I'm getting. Okay. And so now when I look at particular star and I look at the color of the star, then from the color of the star, I can measure the temperature of the star. Okay. Now this is actually an astounding revelation. Before this, before Planck's law, okay, before the advent of thermodynamics, as we know today, statistical mechanics and thermodynamics, the only way we knew how to measure the temperature was put a thermometer in it. And many times it was our fingers which acted as a thermometer. We will dip our finger in the water and say, okay, how hot or cold it is. But just by looking, what is the temperature, we can get the data from the color of the light is something that is actually about 100 years old, 120 years old, something like that. Okay. This understanding is actually very new, although we have been observing the sky since time immemorial, okay, time immortal. We have been looking at the sky, observing the sky, looking at the stars, getting a physical picture of the stars, getting a handle on the physical quantity is something that we have learned only recently, a little more than 100 years. So now you can see that our sun is at around 6000 Kelvin, around 5800 degree Kelvin. Stars which are more red are lower in temperature, and stars which are becoming whiter and then bluer are actually much, much higher in temperature. This is something similar to the candle flame. A red flame is cooler and a blue flame is much hotter. Okay. But mind you, our candle flame is not a perfect black body. It doesn't have that density to be a black body. So the black body temperature doesn't apply to the candle flame. This is something very crucial you should understand. When we look at a candle flame which is yellow in color, it is not as hot as the sun, because the candle flame is not an ideal black body. Okay. Fine. Now, if you want to study astronomy, rather astronomical objects in different wavelengths, then there is a lot of difficulty. And the biggest difficulty is that the light doesn't penetrate the atmosphere. Okay, because our atmosphere is, you know, absorbing, scattering light. And because it is scattering light, absorbing and scattering light, it is blue in color. At the same time, if we want to look at the objects outside the atmosphere, then we have to find some way of going above the atmosphere. Now, if you look at this figure, this is the opacity of the atmosphere to different colors. You can see that the optical regime, by some coincidence of nature, is able to, the light corresponding to the optical frequencies is able to penetrate the atmosphere and reach the surface of the earth. And then there are certain small narrow bands in the infrared where you can see, they are dipped, which are, so those narrow bands in infrared, light falls up to the surface of the earth. And then there is a wide band in the radio where the light falls to the surface of the earth. Now, for all other wavelength bands, the light is scattered away by the atmosphere. Microwave, far infrared, long wavelength radios, they are all reflected back or absorbed. The infrared and microwaves are actually absorbed by the water molecules, carbon dioxide molecules, by the rotation and vibration of these molecules. The radio is reflected by the charged particle in the ionosphere. And if you go to the ultraviolet, X-rays, gamma rays, they are simply scattered by the atmosphere. Okay, all the, all the atoms, they absorb it. And of course, it is good that these ultraviolet rays or X-rays are absorbed by the atmosphere, because had they penetrated the earth, then they would have burnt us and life as we know it wouldn't have existed. Okay, so our life has evolved as per the natural condition that is available to us. Our eyes have adapted well because we are sensitive to the particular small window of the optical regime which penetrates the earth, and sun is such a bright source that we can see what is around us during the daytime. Okay, and so we are able to survive. Okay, but at the same time, it has kept us ignorant for a long time. By absorbing and scattering the other wavelengths, they have kept us ignorant, and our adaptability has also been limited. So there is nothing good or bad about our evolution that we have. It is just that we have learned to exist in the particular state that we are in right now. Okay, so now the important thing is that if we want to observe the sky in other bands, then we have to develop detectors, machines, instruments which can observe these lights, and then we have to, either go above the atmosphere or observe in the bands in which are transparent to the atmosphere. The atmosphere is transparent to it. Okay. So now let's go to the radio band, where we saw that, for a long range, the sky is transparent and these radios fall on the earth. And we have developed over last century, a little bit more than last century, last and a quarter century, you can say, we have developed the radio antenna, we learned about radio waves, but the fact that we learned that, we have learned the fact that radio waves are emitted by cosmic objects as well, like the sun is less than 100 years old. And the story goes that Carl Jansky, the radio engineer, he was told to develop a receiver which will reject all the sources of noise, radio noise, because radio was developing as a means of communication. And this guy, he was always getting a particular background noise which he couldn't remove. And finally, after a lot of experimentation, he came to the conclusion that the source of the noise is the center of our galaxy. Okay, so that was actually the birth of astronomy at another wavelength other than the optical. And then in the Second World War, the radar technology evolved because of communication during the wartime. And after the Second World War, a lot of these engineers, they lost their jobs. Okay, the government said that we don't have money after the war. The economy is in very bad shape. You find your own job. Okay, you do something else. So a bunch of them decided to build radio antenna and start observing the sky. And that was the kick or the development given to the radio astronomy program, which happened in the 50s. Okay. Now the image that you are seeing here is presently the second largest single radio dish in Arecibo. Unfortunately, because of a lot of reasons, due to lack of funds and also lack of maintenance during the pandemic, a big chunk of this radio dish has been destroyed. A lot of maintenance operational presently, a bit and let's see. I hope people get the funds to repair it and bring it back to operation. Okay. Now this is the image, a satellite image of the same radio dish, and you can see the size with respect to the environment. This is actually in a kind of a crater, okay, in a hilly region, and this crater was created by a meteorite. Okay, and this crater has a natural curvature which allowed the structure of this dish to be supported. Otherwise, when the dish was made, we didn't have the technology to support such a massive structure at this level of accuracy. Okay, so this is a radio dish. Okay, and here what we have image is a group of 5 antenna, which is part of the Giant Meter Radio Telescope, the GMRT, and they are, part of 30 antenna, group of 30 antenna, which forms a huge dish in a way, because it is not possible to build one huge dish of the size of 30 kilometers. We have 30 antenna distributed over a region of diameter of 30 kilometers, and combined they form one huge dish with a lot of space in between. But that is a compromise we deal with, because we simply don't have the technology to build a huge telescope of that size. This is located in a place called Khodad near Narayangao, which is near Nashik, about 90 kilometers from Pune. Okay, and this is the biggest radio telescope operating in this particular regime of wavelength. Okay, so the first thing that you have to realize is that the moment you move from the optical regime to any other regime, the instruments change their nature. Okay, when the instruments change their nature, it depends a lot. What instruments we use depends a lot on the nature of the light at that particular energy. So that is why when you are going to the low energy regime, we are looking at radio waves. Light is behaving like a wave, and we are building antenna. Whereas when we come to the optical regime and also the infrared and the ultraviolet regime, we are building cameras. Okay, so now and then at the higher regime, we'll discuss when we go there. Okay, but in the radio, we are looking at very, very low energy of emission. You see, the amount of energy is so low that typically we are dealing with an energy unit called Jansky. Okay, this energy unit, Jansky, used in radio astronomy, is actually named after the engineer who was the first person to measure the radio emission from the center of the galaxy, the engineer called Carl Jansky. Okay, and one Jansky is 10 raised to minus 26 watt. Okay, so you can imagine what energy we are looking at, 10 raised to minus 26. And that too, one Jansky is actually a very high amount of energy. Nowadays, the radio antenna measure regularly in terms of few tens of millijansky. Okay, that is 100 times less than a Jansky. Okay, so now the amount of energy is actually equivalent to the amount of energy that we require in flipping pages of a book. That is the amount of energy that we are measuring. So you can imagine the amount of electronic and mechanical precision that is needed to develop these technologies. So it was not possible for humankind to measure these energies until we have the whole ecosystem of support of electronics, mechanical engineering, and also data processing. So you have to understand and appreciate that the evolution of our knowledge is actually a very complex process where evolution has to happen in all branches of development. Okay, so what are the kinds of objects that we look when we are doing radio astronomy? Now, let me be very clear. I won't be able to give you any exhaustive list of interesting problems which are solved at the different branches. Okay, it's huge. It's what I just try to do is give you a small window for you to start exploring. And the most, from my personal bias, are of material which are thrown out from a compact object, okay, which is normally a black hole. It can be a supermassive black hole, which is a center of a galaxy, or a stellar mass black hole, okay, which is accreting matter from its companion star. And the fun part is when it gathers the matter, it actually throws away the matter in terms of jets. Okay, and these are images, radio images obtained. Okay, since I'm going a bit slow, let me move a bit faster now. You have got an idea that when we are looking at different colors, so radio, infrared, ultraviolet, we are actually looking at different energetics, different level of energy interaction with matter, and that gives us a completely different structure of the object, structural part of the object, as well as the physics or the physical process that is happening out there. Okay, so you can see what we see in radio, these jets we do not see in other wavelengths at all. Okay, we do see in some parts in a very high energy gamma rays also. But anyway, this kind of structure that you see in radio is there only in radio. Okay, and these emissions occur when the charged particle is in the presence of a magnetic field and loses energy when the charged particle, the electric field and the magnetic field of the charged particle is interacting with an already existing magnetic field. Okay, and it comes down the level and it emits photon in the radio band. Okay, fine. And then we have something called pulsars, which are neutron stars, which I will skip for the moment, but they are very dense stars uh, after their death or supernovae, and they are very, very compact objects, and they sometimes, most of the time, have very strong magnetic field, and they also emit in radio as well as in X-rays. Okay, that also. But radio pulsars are again a very, very interesting class of objects which we can see in the radio. And then another very, very important object and a very important source of radio emission is the hydrogen 21 centimeter line. The best, detector of hydrogen gas in the galaxies, the whole distribution of diffuse hydrogen gas in the galaxies is in radio astronomy. Okay, and the hydrogen is so low. Okay, it is only seen in this particular 21 centimeter wavelength. Okay, now let me move. Now let's go to the microwave regime, and you can see the microwave is not reaching the Earth because of the opaqueness or the opacity of the atmosphere, and hence we have to build satellites to go above the atmosphere. And the most interesting phenomena or the source of microwave emission is a microwave background radiation, cosmic microwave background radiation. Okay, and this is a relic of the Big Bang. So when the Big Bang happened, the universe was a point mass, a singularity, and then it expanded. As it expanded, it cooled down, and the energy, the photon at that time of Big Bang was extremely hot. And now, after 14 billion years of expansion, it has cooled down to 3 degree Kelvin. And this temperature is measured in the microwave regime. If you remember the curves that I showed you of Planck's distribution, that 5000 degree Kelvin is in the optical regime, 3000 is in the infrared regime, you come down to 3 Kelvin. Okay, another 1000 times less is the temperature. That goes to the microwave regime. Okay, and microwave regime is also the regime in which a lot of radio communication happens actually. Both the radio wave and the microwave, lot of communication happens. Okay, so the relic of a Big Bang is observed only if you go above the atmosphere and you use satellites to see the microwave radiation. Okay, then again let's come to the next regime, which is the infrared regime. Okay, infrared, as you know by now, is less hot than the optical regime, and you should be able to guess immediately that an object which is less hot than the star is a star that is not born yet, which is still in the formation, which is known as the young stellar object. So if we want to study the formation of stars, then infrared regime is the regime that we are looking at. Okay, and also when we are looking at the interstellar dust, interstellar matter, the space between the stars, which we assume to be a vacuum, is not exactly vacuum. A very, very interesting physical process. I mean, not only physical processes, chemical processes are happening out there, and they are also lowering temperature, this interstellar medium, but higher than the cosmic microwave background radiation, and they are observed in the infrared band. Now we have already discussed the optical regime of sun and other stars. Now let's go to the ultraviolet regime. Ultraviolet is more energetic. So when we are looking at events like supernova remnants, young supernova remnants and all, then the ultraviolet regime gives us the dynamics at energetics higher than say 10,000 degrees Celsius or higher, 10,000 Kelvin, 100,000 Kelvin. Okay, that is the range in which we are looking at when we are looking at the ultraviolet regime. Also, there are stars, very hot stars, which peak at the ultraviolet regime. So the study of galaxies at the ultraviolet regime reveals a lot about the galactic dynamics and the star form, the stellar population of those galaxies. Okay, and in fact, recently from Astrosat, a very interesting result by our colleagues in IUCAA, Professor Kanak Shaha and his collaborators, they have observed ultraviolet emission from a very, very distant galaxy, very high redshift galaxy. So this gives you an information of the galactic dynamics happening at that old history, okay, at the very early phase of the universe. So this is again a very, very interesting branch, but a very difficult branch to study because our interstellar medium acts like an absorber of the ultraviolet rays. So it is actually a very difficult study, and we have to, develop very sensitive instruments for ultraviolet spectroscopy. Now, take one example is this. Look at this object. The bottom image is in the optical regime, and the top image in the ultraviolet regime. In the bottom regime, you can see a particular star that we are looking at. In the ultraviolet regime, you can see a trail of gas, a trail of dust behind it, a hot dust, which is not visible in the optical, but visible in the ultraviolet. And this immediately gives you the path that this star has covered in the history. Okay, so this is another example of how, by broadening our range of observation, we can get newer information, newer structures. Okay, now let's go to the X-ray regime, and I will just mention our good old Astrosat, which is now I think 5 years old now. Okay, the Indian X-ray satellite is not just X-ray; it is ultraviolet. It has ultraviolet imaging telescope also, and various bands of X-rays. So now, as we saw, that since X-rays are not penetrating the atmosphere, they have to be flown above the atmosphere, and so the best bet is to have a satellite observatory, and Astrosat is one such Indian satellite which has been doing very good job of observing the sky in the X-rays and gamma rays, and it is still operational. Okay. Now, the kind of sources that we look at the X-rays are extremely energetic processes. Okay, which has the sources that emit huge amount of energy, because X-rays are 1,000 times stronger than the optical regime. Okay, so now we are looking at temperatures which are kind of million degrees, and in fact it is very difficult to have a gas at million degrees. It's called plasma, and that makes life more difficult to understand and to make a theoretical prediction of what is happening. But the kind of sources that we observe are mainly very compact objects like neutron stars and black holes, which have very strong gravitational field because they are extremely dense objects, And this gravitational field attracts matter from the environment, and the matter that falls in loses huge amount of energy, gravitational energy, because the gravitational energy loss is huge. And this amount of energy, when emitted in electromagnetic radiation, it is emitted in the X-rays. Okay. So now when we are looking at these objects in X-rays, we are looking at the very high energy physical phenomena that is happening in this universe. And they are mostly not replicable in our laboratories yet. Okay. So although people are developing tools to develop similar physical scenario in the laboratory, but still we have not reached that level of density and that level of intensity of X-rays. Okay, so and X-ray astronomy is my very favorite subject. I am specialized in this particular branch of work. So we are always dealing with extra binary stars and their accretion processes and the physical processes that go along with them. Okay. So what happens is that, this is just, since I don't have much time, I'll just give a glimpse. Okay, these are the compact object in the center, and matter falls, spirals in the form of a galactic disk, which is shown by these, you know, cross section that you see, the brown cross section that you see, and matter is falling in, okay, into the compact object. And the interesting thing is that when matter falls in, as I said, mentioned before, they are also ejected out in the form of radio, and here we have the radio images of the same object. Okay, so the interesting thing that you have to appreciate is that the same object is visible in the lowest regime of the electromagnetic radiation, lowest energy, and the highest energy. Okay, and they are coupled together. This makes the physical understanding of these objects so interesting, at the same time so difficult. So these are actually the cutting edge of research that we guys are doing. I mean, we are all over the world, we are trying to build theoretical understanding of what is happening out here. So these are very, very active fields of research right now. And then I will just mention the fact that we had talked about composite images in the beginning, right? So now let's look at the Crab Nebula. Okay, the Crab Nebula, this is the last thing I'm going to talk about. Look at the image of Crab Nebula in X-rays. This is a structure of the supernova remnant. The supernova happened 1,000 years back, and now the high energy phenomena, the high energy is emitted from this kind of a structure. You can see it, right? Now let's go to the ultraviolet. Now see how the structure has changed a bit. It has some semblance to the previous extra structure. Okay. Now let's see the structure in the optical. This image is from Hubble. But mind you, first thing that you should, let's go back to the X-ray. The color that you see, okay, it's kind of purplish pink, okay, pinkish purplish, okay. This is definitely a false color because the actual image is in X-rays. So please understand the concept of false color images. Our eyes cannot detect X-rays. We don't have any sensation of what X-ray does because our nervous system cannot detect it. So we have converted the X-rays into a color that we can understand. Then the ultraviolet we have converted into blue. This is from another satellite observatory called External Newton, a European satellite observatory. It is in ultraviolet and X-rays. Okay, but now this is a Hubble diagram, Hubble image of the same object, and look at the structure. How at this energy the whole structure has changed completely. This is also a false color image. I can generate this particular image in any shade of green, blue, yellow, red. And this image is an infrared image. Now we are going to the low energy, the low temperature component of the same structure. And this ultimately is the radio image of the same object. And when we combine all of them, this is a composite image of the Crab Nebula from the X-rays to the radio waves. So what it gives us is the information about the structure of different energetics happening, the different physical phenomena happening in the X-ray regime, which is 1,000 times stronger than the optical regime, to the radio regime, which is 10,000 times, 100,000 and million times less energetic than the optical regime. So this kind of image is possible only today. Before that, we didn't have the ability to create such images. We didn't have the ability to see these objects in their full glory. So we should be thankful that we are living in an era where we can see these images spanning the whole electromagnetic spectrum and understand, at least try to understand what is happening in the physical scenario out there. And the last slide that I will show is this is a image. This is an image of the black hole M87, which became very famous last year. But one of the things that is lost in all the reports that I see is that this is again a false color image. I have come across many students asking me, why is the object yellow? Sorry, orange and yellow. Okay, the fact is that this is also a false color image, and the actual color is actually in radio. This is 230 to 4. The Event Horizon Telescope operates from 230 to 450 gigahertz. Okay, so please understand this image, which is everywhere. The M87 black hole. Okay, everybody understands. This is the image of a black hole. But this is again a false color image, and I've gone through the press releases and all the reports of this particular object, and I have not come across anywhere where they actually mention specifically that this is a radio image. It's unfortunate how the media, sells news, sells facts without giving a proper understanding. So all of us need to develop this attitude to go beyond what is popularly reported and unearth what are the facts. Okay. Now, before I end, I will ask a very favorite question of mine. What is the color of man? Okay, now this is a very, very politically loaded question when it comes to race, when it comes to racial discrimination, when it comes to sensitivity about other people. We have developed our human society in terms of, white race, brown race, yellow race, black race. But let's go a little bit deeper in our understanding that what actually is the color of man. Now the thing is, if you go through what we have been talking about, then you will immediately understand that we are also black bodies, right? We have a temperature. Our temperature is 300 Kelvin. So we are also emitting at a particular wavelength, range of wavelength. And our wavelength is actually infrared. Okay. And had our eyes been sensitive to only the infrared regime, where our emission peaks, then all of us would have the same color. Because all of us have the same temperature. Unless we are running a fever. And if we had a fever, we wouldn't need a thermometer to measure it. We will be able to discern a person getting feverish just by looking at the change in the color of that person. Unfortunately, we do not have the eyes to measure what we emit ourselves. We have eyes to measure what we reflect and scatter when the source of light is some other light. That is why, in the absence of any other source of light, we can't see each other. In dark, we are invisible to each other because we cannot see our infrared emission. But in the presence of some other source of light, we are scattering the light at different colors, which is a function of the molecules, a very complex function of the molecular distribution, molecular properties, and we are able to see that. So let's appreciate this fact that we have to broaden our horizon and look at us with a broader, much broader perspective and see how what we actually are and how we are different from each other and how we are similar to each other and how we are equivalent to each other. With that, I will end the talk today. Okay, thank you.
Uh, First of all, sir, I'm very thankful to have this very, very interesting and very informative talk, which starts from basics, like I mean, from where the light has been started. I mean, from where the light is coming to the various energy levels of the light, starting from radio to the to about infrared and the visible region. So, and first of all, I mean, it was like a quick recap for me for my entire physics course, which I have done. I mean, it was really, really interesting to hear you about this thing. Sir, should we go with the questions now? So,
Yeah, if there's any question, I'll be happy to
yes, yes,
respond.
yes, yes, yes. I mean, there
provided
are like
people
a
are
lot of
awake, provided
no,
people are still awake.
yes, yes. No, no, actually, there are questions in the chat box, so I will go one by one. Parag will unmute that person, and we will have one-to-one interaction with them. Okay. So
Yeah,
the
please.
first question I will go with is I will only take the talk related question. So
Yeah,
the questions which are not related to talk, I might keep it at the end, or
yeah,
depending upon the
sure.
time whether we can take it
Yeah,
or not.
yeah, we can take a
Okay?
call later.
Yeah. So the first question is by Samay Chaudhary. Parag, can you just unmute Samay? The question is, how is photon made during losing the energy? So this is very
Ah,
basic question. I guess the
yeah.
I just repeat the question. How is the photon made during losing the energy?
Okay. To have a basic understanding, you have to understand something called quantum electrodynamics. Okay. You have to go through Richard Feynman diagrams. Okay. But the basic idea is that, you know, when an electron has an electrical field around it because it is negatively charged, and then it is in the presence of electromagnetic field, when it is losing energy, that electric field, the vibration of when an electron is accelerating, okay, or decelerating. Okay, whenever say an electron is oscillating, right? So now acceleration, deceleration is is changing a cause in the structure of its electric field structure. Okay, the electric field is changing as a function of time. Okay, and this vibration that is happening in the electric field, this is the classical mechanic understanding of it. The quantum mechanic understanding, you have to go through quantum electrodynamics. That I think, I mean, we will require much more study. There are a lot of more things that has to be explained before one can really understand the quantum mechanics of it. But you can understand that electron is actually, throwing away a photon and going down in energy. It's like, suppose a very crude analogy is that I am running, and if I throw a ball forward, then by Newton's third law, I will be thrown backward. Okay, so I will lose energy and the ball will gain the energy. Now imagine that ball is a photon. Okay, so that photon is ejected out, and the electron which was throwing it will go down in energy. It's a kind of a crude analogy, but at certain level, at the first level, it helps you in giving a picture of the understanding.
Okay. Uh, Sarag, have you unmuted Samay?
Yeah, yeah.
Okay.
1 second. I'll just unmute him again. Yes, he's there.
Okay, Samay.
Thank you, sir.
Yeah. So, do you have any more question? I mean, any more clarification needed on this one, or
No,
it's fine for you? Okay. Okay. So we'll go for the next question. Next question is by Mohammad Kamran. The question is: the galaxies look stationary, so why do scientists say that they rotate? Can a star turn into a planet? This is like very very basic question, I guess. So the question is, when we look at the galaxy, it looks like very stationary. So why scientists say that it is rotating?
Okay. Now the thing is, you see, let's understand. How do you understand motion? First and foremost, when we look at an object that is moving, we look at the change in the angle from our point of view. Okay, that is how that is the first understanding of motion, right?
Yeah.
Now, okay, so now you look at say an aeroplane moving in the sky or a car moving along the road. How does it change? From our point of view, the angle at which we are looking at a particular object is moving is changing, right? Now, when it comes, as we start looking at objects which are moving at a slower speed, or are very far away from us, they are both having the same effect where the angular change is very small, right? So now the thing is, when the change in the angle at which we are looking at is very small, then we have to look at other phenomena. Okay, now I don't know which class you are in. The person who asked this question, can you tell me which class you are in? He or she is in?
So I'm in class ninth.
Okay, class 9th. Okay, fine. Now the thing is, I don't think you have come across something called Doppler's effect. Okay, so now a very simple example of Doppler's effect is that I mean, if you go to class 11, 12, you'll definitely study. I don't know whether it's a part of a class 10 syllabus or not. I don't remember. The thing is, have some imagine some musical instrument, okay, or a whistle. Take for example a whistle of a train. When it is moving towards you, the frequency changes. Okay, it becomes more shrill. Okay, and then when it crosses you, it moves away from you, the frequency again changes, it becomes less shrill. So the frequency of the sound changes, okay, with the speed of the object. Is that clear? So what we need to measure is the Doppler effect happening on the frequency of the light, or as we saw, the frequency of the light is color of the light. Okay, so now we have light, we expect light to come at a particular energy. You know that we are talking about transitions, right? From one level to another level, we know what the transition is going to be like. Now, if an object is moving, then that transition frequency, that energy or the frequency of that light is also changed. Okay, if the object that I'm observing is moving with a certain speed. Now, when I measure the change in the frequency of the light, I am measuring the speed of the object. So, when I'm measuring the speed of the galaxy, a distant galaxy, actually what I'm measuring is at different parts of the galaxy, different points of the galaxy, I'm measuring the light and seeing how is the frequency of the light shifted from its expected frequency. And that shift is the Doppler shift. And from that Doppler shift, I am measuring the velocity or the change in speed. Okay, change in speed from the stationary state.
Okay.
Is this clear now?
Yes, sir. I hope it is clear.
Okay, what was the second part of the question?
Uh, yeah, Kamran, can you just go ahead with the second part of the question?
Yes, I want to ask that can a star change into a planet, a big
A
star?
star, a star cannot change into a planet. Okay, actually, planet formation is intimately related to star formation. What happens is that when a star forms, again, in the process of forming, it forms an accretion disk around it. The matter falls into a star in a spiral manner. Okay, and when a
Yeah.
star forms from the debris of the accretion disk, the planets are formed. Okay, so planets are
Yes, I got
slightly,
it. Got.
yeah. So a star doesn't change into a planet, but from the debris of the planet formation, planet forming accretion disk, the star forming accretion disk, the planets are formed.
Okay.
Okay, yes, yes, sir. Thank you, sir.
Yeah. So the next question is by Arohan Kala. Para, can you just unmute him? The question is, if the universe is only 14 or like 13.7 billion years old, then how is it possible to see up to 92 billion years?
It is not possible.
Yeah, I mean, there is a
Okay,
question by
we
Arohan.
cannot go. You cannot go back to 92 billion light years.
Yeah.
Okay, it is defying the Big Bang. Okay, so in that case, this observation is something that doesn't agree with the Big Bang theory. That's it. How
Okay.
to explain that? That's a different ballgame altogether.
Okay.
Yeah.
Yeah. So I'll just go to the next question. This. Okay. So the again the question from Arohan again. If we see a place in different wavelengths, then can we at least know the presence of a black hole? So basically, if we want to find, I mean, how to find a black hole? Maybe basically this is the basic question might be there.
Yeah. You see, understand one thing, that a black hole by itself doesn't emit any light. That is why it is called a black hole. You see, once any object, including light, photons, crosses the event horizon, it it cannot come back. The only way to observe a black hole is to look at other objects which are falling into it. Okay, so there are two. I mean, rather one way of looking at what shall I say, discovering a black hole, and that is find an object which is falling into a black hole and look at the energetics of it. Okay. So now, as I said, when you have a galactic nuclei, which is a supermassive black hole, and accreting matter from the environment, then we look at the energetics. The matter is falling onto it, and it is getting converted to light. Okay. Or if I have a stellar mass black hole, say 10 mass black hole, which is accreting matter from the companion star. Okay. Then it the star is giving away, the companion star is giving away the mass, and that mass is falling into the black hole. That gravitational energy is getting lost, and that is getting emitted into X-rays. That amount of energy lost is so high that it is emitting into X-rays. Okay, so that is one way of finding a black hole. That okay, we are looking at the energetics of the object moving around it. But mind you, finally, the clinching argument of a black hole is when we know the exact mass of the object and the size of the object. Okay. Now, for that, we have to understand the dynamics of it. Okay. So, in case of stellar mass black hole, the clinching argument of a black hole will be when I know the mass of the compact object and I know the mass of the companion star and I measure the periodicity. Okay. And that from Newton's laws, which can be expressed in terms of Kepler's laws, I measure what is the size of the black hole. Okay. So, and this is also exploited, this idea is exploited in coming to the conclusion that at the center of our galaxy, there is a black hole. We have concluded that there is a black hole. Okay. But it is not a creating matter. Fine. Then how do you measure it? The measurement requires very long measurement of many stars around it. And we measure the rotation of the stars around the center of the galaxy. Okay. And when we measure that, then using Newton's laws of gravity or Kepler's laws, Newton's laws of gravity are expressed in Kepler's laws. From there, we get an estimate of the mass and the size of the central object. Okay. And from there, we get the estimate of how compact it is. And if the compactness is higher than the critical compactness of a black hole, then we come to a conclusion, okay, it's a black hole. So in case of our uh, galactic center, we didn't really look at X-rays, okay, for determining it's a black hole. We just saw what is in the optical only, how are the stars near the center moving. Okay, imagine a similar scenario of planets moving around the sun. We are looking at the stars moving around the center of the galaxy, the closest one. Okay, and then from the dynamics of it, we came to the conclusion that here the amount of mass confined in that small region can only be explained if it is a black hole.
Like basically, like we have to look around the region, not in the exact region.
Exactly, we have to look at around the region.
So,
Exactly.
sir, if
Yes.
Yes.
we can know the presence of a black hole, if it is feeding on a star.
Yeah, I mean that is one of the ways that when it is in a binary system with another star, then the other star is losing matter. Stars lose matter in many ways. Our sun is also losing matter continuously. There are solar winds, okay, throws out matter and all those things. Now that matter which is being thrown out is captured by the compact object, and the amount of energy, the gravitational energy that this matter loses is measured by us, and then we can come to a conclusion, okay, this can happen only if it is a black hole or neutron star or whatever. Okay.
Okay, sir. Thank you, sir.
Okay. Thank you, Arun. The next question, sir. Actually, I will like to ask, like, how much time you have for
I
this,
have,
because
it's okay, not
we
an
can.
issue.
Okay.
Yes.
Okay.
I am open to questions all the time.
Okay, fine. So, so the next question is from Sachin. The question is like, which wavelength we should look in order to study the condition of early universe. Like, suppose if we have to study about the early universe, maybe just after Big Bang, or like maybe in the inflation region, maybe. So, if you have to study that kind of region, which prominent wavelength that we should look for?
Well, one prominent wavelength is the microwave, okay, but at the same time, we have to look in all possible wavelengths, from infrared to X-rays. You see, I really cannot go into too much of detail out right now, but the thing is that all of these wavelengths have some phenomena, some physical scenario, which is related to the Big Bang, okay, or the larger structure of the universe. Okay, so that way, some infrared, some gamma rays, very high energy gamma rays. Today I didn't talk about the gamma rays at all because I knew I wouldn't have the time.
Right.
Okay, higher than X-rays, the gamma rays. Okay, so also the diffuse X-rays, X-ray diffuse background, the infrared, okay, and the microwave, from which we can understand the magnetic structure of the galaxy, of our galaxy. Okay, so there are many phenomena that are available in all the wavebands. Okay, some phenomena associate with the Big Bang. But yes, the predominant feature is the microwave, where the Wilkinson Observatory has done a terrific job, WMAP. Before that, it was Kobe. That gave us the first understanding not only of the Big Bang, but also the early formation of the galaxies, where matter was started to cluster. So that was a deviation from the uniformity of the Big Bang, which Kobe was able to measure. It was an amazing measurement. And that was fine-tuned to great extent by WMAP. So that is the primary region that we are looking at. But at the same time, radio sources, radio emission, the hydrogen 21 centimeter line, how the
Right.
dynamics of the hydrogen 21 centimeter line, the infrared, then high energy gamma rays, they all contribute in some way or the other. Optical regime in this way can contribute only if we're looking at very high redshift galaxies. Same with ultraviolet. When we are looking at redshift of 10, 11, and if we can find an ultraviolet radiation from them, it's amazing. And redshift of 10 or 11 is very, very early universe. So you see, they are also contributing to understand.
So,
Okay, sir.
Sachin,
Thank you,
if
sir.
you have any more doubt, you can.
Uh,
If you are satisfied, then you can sign, or else you can re-question it if you want to ask.
and sir, like if I talk about specifically about energy during early times, so I mean, which wavelength will be much useful in determining the initial energy? I mean, roughly or approximately the
You
initial
see,
energy.
again, as I said, if I'm looking at able to measure ultraviolet from very high redshift galaxy, then that is useful. Otherwise, I will look at the cosmic microwave background radiation, CMBR, which is in the microwave. Okay. At the same time, if I'm looking at dynamics, hydrogen line, 21 centimeter line, okay, and hydrogen dynamics of hydrogen from very high redshift galaxies, okay, and optical radiation from very high redshift galaxies, then they are also useful. So it depends on the context. There is no one particular way to do it.
So basically, every different wavelength has some information inbuilt in it. So we have to
Exactly.
study
When
all the
we,
wavelengths simultaneously to get the actual picture.
yeah. So as I said, we have to get a composite picture. You know.
Right.
Yeah.
So the next question is from Samay
Thank you, sir.
Chaudhary again. Yeah. Thank you, Sachin. The next question is from Samay Chaudhary again. So the question is, what is the actual color and temperature of Crab Nebula? So like, I mean, you had shown the different images of Crab Nebula. So what
Well,
can be the actual or
there
like
is
the final
nothing.
color of Crab Nebula?
There is no one color. There is no one final color. It's a composition of everything. Okay, we have to broaden our horizon. Yeah,
Yeah.
it's the guy you can't say कि ये इसका actual color है. No, and
Right.
it's also a
Actually,
function of time.
yeah.
What
Right.
I'm
I mean,
seeing today, when the supernova happened, it has a different structure and the color distribution will be totally different.
right. Actually, this is the main crux of this talk is all about, I guess. Right.
There is no one actual final answer. In certain manner in schools where we are told कि ये question है और इसका ये actual final answer है.
Right.
Okay, but unfortunately, the universe doesn't follow that law. Our society follows that law. Okay, so we
Okay.
don't have. It's always depending on the context.
Right. So the next question, maybe we will take few more questions from Zoom, and then we will go for YouTube. There maybe we will take 4 5 questions, and then we will
Yeah,
end
yeah,
for
sure.
this talk. So the next question is by Shaurya Joshi. Farah, can you just unmute her? Yes. Her or him, Shaurya or Shaurya, depends. Like the question is, why is the image of black hole of M87 in radio region basically is yellow in color? Like, so I mean, why not any other particular color? Why only yellow color for representing radio emission?
Samir,
Because I think,
sorry, sir, to disturb you. Samir, can
Yeah.
you repeat the name again?
yeah,
I can't see his name.
Shaurya Joshi. Maybe it has
He
left.
must have left. Yeah, he
Yeah.
must have left.
So,
Yeah, no
but still
problem.
the
okay.
question is interesting.
Anyway,
We
but the
can go with the
question,
question.
yeah, question is interesting. I think it is just got to do with aesthetics. You see, when we are having a black background, yellow orange gives the best contrast for our eyes. Okay, if I have a blue image or a green image, then it will not give that good, that pleasing effect to our eyes in a black background. This I have seen for other objects also. When you do image analysis, it is very useful to see things in yellow to orange. And you see, I think another question is of uniformity. Now, what happens is that I think it was a very, very, what shall I say, uh, what a well thought out decision from the community of the astronomers who gave the image, that they will give out only one color image so that there is no confusion in the social media. As you know, in social media, how fake news spreads. So I guess
Right.
to prevent any such spreading of any misinformation, okay, they decided to have, I mean, release images which are all of the same color. But in principle, you can render these image in any different color. Okay, but this is
Okay.
my conjecture. I mean, I have no proof for it.
So maybe the final question from Zoom. Uh, the question is from Arnav basically. Parag, can you just unmute him? Arnav, if he's there. Okay. So the question is, if Bohr model shows this phenomenon of energy level, then can it be connected with the Raman effect as it causes scattering?
You see,
So
Bohr's model deals with your electrostatic energy between the positively charged nucleus and the negatively charged electron. Okay, whereas the Raman effect has got to deal with the vibration levels. Okay, so they are actually different phenomena, but they are kind of related in the sense that they are all discrete levels. Okay, so you can say the energetics of vibration level is different, energetics of no rotation level is also different. Okay, there are lower level. Then it comes to the vibration levels. Okay, then comes the electronic levels. Okay, so they are connected in the sense that they are from the same molecule, but the physics that is happening is actually very different. Other than the fact that they are all quantized effects, and they give rise to completely different in different scenarios altogether.
so can you just unmute Arnav, Parag? Maybe if he's there. Arnav, can you hear us?
He's already, wait, I
Uh,
already unmuted him. He has muted himself again.
okay.
Okay, I have
Yeah.
another short question.
Yeah.
Before I was before in the meeting, I heard Sir mention about uh, uh, how a photon is created when an electron jumps from its energy level. So I just wanted to ask whether it has anything to do with the photon and electron pairing.
It has got everything to do with that. Okay,
No, because
basically,
I had read about it
the
briefly, so I didn't know for sure.
yeah, yeah. For this, for ultimately, it is your interaction between matter and photon, matter and radiation. Okay, so
Okay,
for that detailed understanding, you have to understand the quantum mechanics of
right,
it.
right.
But yes, definitely, it is related to that one.
Okay,
Obviously,
sir.
but it is not so simple. You have to go through a lot of mathematics. You have to develop a lot of intuitive, counterintuitive logic, which is
The Feynman
you know
lectures.
Feynman's diagrams, not
Yes,
lectures, Feynman
Feynman's
diagrams. Okay,
diagrams.
yeah. Okay, so you have to understand Feynman diagrams, and it can have a lot of counterintuitive logic which comes with quantum mechanics. So first we have to understand quantum mechanics, and then one can go into it. Because what my problem with the popular science is that they try to explain things with a lot of analogies which are not entirely correct and can lead to mistaken analogy, mistaken understanding. So one has to be very careful about that. That's all. For example, this in the picture of a man running and throwing a ball, and Newton's law throwing him back, is not a very correct analogy, but at a very gross scale, it can explain to you, okay, something like this happens, but not exactly.
okay.
Okay,
Okay, sir.
yeah.
Thank you.
Okay. I guess. Uh, okay. Just a second. Let me go to the question again. Okay. I will take one interesting YouTube question after this.
Sure.
So the question is by Shrikant. The question is like we always talk about frequencies and wavelength of light wave in optical region, which is due to the electric field vector. Okay. So do we have any sensor or do scientists study the magnetic field part of the electromagnetic spectrum? Like I mean,
Please,
do you want me to repeat
can
the
you please
question?
repeat? I lost
Yeah,
the
yeah.
internet.
Yes.
Yeah, we
Actually,
lost the
actually,
internet connection.
it is a long question. So the question is, we always
Yeah.
talk about frequency and wavelength of light wave, which is practically, which is basically due to the electric field vector. Okay, of the basically the this is due to the electric field transition of electrons. So do we have any sensor or do scientists study the magnetic field part of the electromagnetic spectrum? Mm, no, actually
Well, this
actually
is
I
actually a very, very good question.
yeah.
This is actually a very, very good question. But the fact is that the electric field is definitely more dominant. Okay. So when it comes to building detectors and all, the antenna, we normally talk about when we design an antenna. Please understand one thing. I don't know what is the level of the student, but if he understands the little bit, if he knows quantum mechanics, he'll understand that light photon has both wave-like and particle-like nature. Okay. Now, when it comes to the wave-like nature, normally all the detectors take into account the electric field vector. When it comes to the
Sir,
optical
actually we
level,
missed your voice.
optic.
Can you just repeat again what you
Oh,
said?
I'm sorry.
Just we
I'm very
clear.
sorry. Can you
Yes,
hear me now?
yes, we can hear you.
Can you hear me now?
Yes,
Okay.
please
The
continue.
thing is, when it comes to the low energy regime, about radio microwave, we deal with the wave nature of light. Okay. And there we are dealing with the vibrating field, and mostly our dishes, radio dishes and all, they work mostly on the electric field. Okay. And because magnetic field is coupling is less and electric field is stronger, and they are always complementary to each other. So if you measure the electric field, it works for the magnetic field also. Okay. When it comes to the optical regime, okay, now before coming to optical regime, let me go to the X-ray regime. Okay. In X-rays, we actually treat light as photons, as particles, not as a wave. Okay. So one photon comes and hits the detector and we measure the energy. When it comes to the radio, we are not measuring individual photon energies. We are measuring the energy of the wave, which can have billions of photons. Okay. When it comes to the X-rays and gamma rays, we are dealing with the particle nature of light. One gamma ray, okay, hits the detector, we measure it like we measure a one ball. Suppose somebody is throwing one ball after another, we catch one ball, count it. We catch another ball, count it. Okay, that is exactly how our X-ray and gamma ray detectors are made. Okay, so there we are not dealing with the electric and magnetic field at all. Now, when it comes to the optical regime, which is bang in the middle, from radio to gamma rays, which is bang in the middle, and the interesting thing is our detectors actually make use of both the wave nature and the particle nature of light. When we are dealing with the optics, the lens, we are dealing with the wave nature of light. And the detector that we have behind the optics, earlier it used to be chemical detectors, nowadays you have electronic detectors, right? These detectors actually make use of the particle nature of light. They don't measure the electric field. They measure the quantum of energy. Quantum energy hits, you assume a photon, a CCD detector or a CMOS detector, it absorbs a photon, records it. Okay. So the optical regime, the camera makes use both of the wave nature and the particle nature. Higher than optical regime, the X-ray and the gamma rays, we are making use only of the particle nature. Lower at microwave and radio, we are making use only of the wave nature of light.
Okay. I guess this was very briefly explained by sir. So I I think we should stop here because there are like many questions are there, but still, I mean, since last two
Yeah.
hours we are. So I would like to thank you, sir, for this very interesting talk, and I'm sure definitely participants had also enjoyed this talk, and I mean, this is a continuous learning process. We are going to have, I mean, we are going to host other scientists from different backgrounds also. So just stay connected to our educators. We will definitely going to have other free webinars where you can join and ask questions related to their field of, I mean, their expertise over there. But before that, I will just like to thank Manojendu sir for this excellent talk. And I mean, we are just glad to have you over here because this was our first guest talk over here, and it was really amazing to have you on this platform. Thanks a
Yeah,
lot, sir.
it is
Yeah,
my
sir.
pleasure, and I mean, I hope people gain something out of it. There'll be some, they'll take back something from
Yes, yes,
this. I hope
right,
everyone. That's all
right,
I can hope
right,
for.
right.
And thank you for
Yeah.
inviting me here. It is my pleasure to, be associated with students. I love to be associated with students all the time and face
Yes,
their questions.
yes, yes.
That is
Uh,
how actually I learn, frankly speaking.
right, right. Okay. So before I will just wind up this meeting, I just wanted to announce about the next talk. So
Yeah.
the next talk, I mean, sir, can you just stop sharing your screen so that I can share my screen over here?
I don't think I'm sharing the screen
Okay,
now
okay,
here.
okay, fine,
Yeah.
fine, fine, fine. Okay.
Yeah.
So let me give you the poster of our next talk. Just a second. Okay. So the next talk is a very interesting talk, which is been the I mean the speaker for the next talk is Dr. Aniket Sue. Uh, Let me share you the poster. So I hope you can see the screen now. And the talk topic is very interesting. It's about astrology and astronomy. So hope, I mean, if like most of you, if you go through your daily horoscope, this is the topic that you should be, present for the talk. So this is like very interesting topic, and we are going to host this free webinar on 11th of October at morning 11 a.m. And the speaker for this talk is Dr. Aniket Sue. He is basically a general secretary for International Olympiad on astronomy and astrophysics. So he is the one who is driving force. I mean, he is one of the driving force beyond the, I mean, for the International Olympiads in India. Okay. So this is our next talk. I hope to see all of you, those who are here, those who are present on YouTube, those who are present on Facebook, to be present on this next webinar, which is on 11th of October. So by this, I just end this meeting, and I just thank once again for to Dr. Manojendu sir. By this, I hope most of the participants who are here have really gained much of the basic knowledge of astrophysics, because most of the basic astrophysics was covered in this talk itself. So I would like to thank you, sir, a lot. By this, I request all of you to leave this meeting, and we can join again on 11th of October.